Hey everybody! The purpose of this video is to get us some solutions to the Gambler's Ruin quiz. Let me make it a little bit bigger so it's easier to see. And basically I want to use Excel to do this because this computation gets a little bit tedious to do in the TI. Of course you may have done it in the TI, that's totally fine. If you're used to the TI, it makes perfect sense. So the basic idea, basic premise of the game you already understand in that you have to play craps, bet $1, and keep playing until you win. And the betting scheme is outlined for you in the quiz. What I've done here is instituted it mathematically. So if it takes you one, suppose for example that you play the game one time, bet your $1, and then it takes you one roll to win back. So you won in the first roll. Whether it's, I shouldn't say the first roll, I should say number of games to win $1, because it might take more than one roll if you're familiar with craps, but it's all the same. So if you win in that first round, it costs you $1 to win $1. So what I've got here is I'm going to keep changing these little numbers here. It costs you $1 to win $1. So you break even, essentially, but it costs you $1 to win $1. The chance of that happening, as is instituted on the quiz, is about just under 50%, 0.492929. I'll be happy to sit down with anybody and explain why that is. It's actually really, really cool. Now, if you just use this for the average, you can calculate the average by doing this times this. And that's exactly what the average is. It's the sum of all the random variables times the probability of that random variable. And the average would be 0.49, which means it costs about a half a buck to make a buck. The problem, of course, is that that's not complete because this column, as a probability distribution, needs to sum to 100%. Because half the time, a little more than half the time actually, you're going to lose on the first one, about 0.508 or 0.509, I guess, or excuse me, 0.507. 50.7% of the time you're going to lose, which means it's going to take you a second roll, but you double down your bet. So now you're in the hole $3. Now the chance of that happening is about 25%. Now think about why. You had to first lose, which happens about half the time, and then you have to win, which also happens about half the time. So that's a half of a half, or about 25%. So now if you do this, what I did in this column right here is just, again, this times this gives you this. Now what I haven't been showing you over here is the average column. I'm keeping a running total of what it's going to cost. Check this out. If you add these guys together, you get this. So now if you account for 2 games, if you win on the first one or if you lose on the first one and win on the second, it's going to cost you an average of about $1.25 to win back your $1. But once again, this is not complete because we've got about 25% that's not accounted for. Because you could lose on both the first games. It doesn't happen it's not that an infrequent event. So it might take you 3 games, in which case you've now bet $4, which means you're now totally in the hole 7. The chance of that happening is, again, about a half of what it was before. So if we continue this pattern, there's your x times p of x. Notice these chunks are getting bigger. Not a coincidence, friends. That adds to the average. So now it's going to cost you about $2 to earn back your $1. So you see what's happening. It's costing you more money with each successive turn. Now some of you are going to say, yeah, but you don't take 3 turns to win, but 12% of the time, 13% of the time. Yes, but we're talking about an average here, friends. We're talking about an average. This can happen 12% on average, which means 1 in 8 times you try this is going to happen. And guess what? 1 in 16 times you try it, it's going to take you 4 rolls, and it's going to cost you $15 to win it back. Now watch what happens again. It went up again. My first question is, what is the Gambler's Ruin? And you're beginning to see it. You're beginning to see it. It's a scenario. Hopefully you Googled it and found it. It's a scenario by which you can win a fixed amount of money by planning your bets accordingly. The problem is, on average, it takes an exponentially large amount of money to actually do this. The next question is, what's the chance you can do it within 10 rolls? Well, within 10 rolls, this is the distribution here. Let's go ahead and make these black. They're already there. So, of course, it's not gonna happen but 1 in 1,000 times that it's going to take you 10 rolls to get your $1 back. But that does happen on average and must be accounted for in the average. So when you actually look at the average, which is right here now, let's go ahead and make that yellow. That's what it's going to cost you on average if you take up to 10 rolls to win. But the problem is you're not done yet. Because if you sum up, hi Daniel, if you sum up those probabilities, they don't sum to 100%. You're off by about a tenth of a percent. And the reason is because you're not done after 10 outcomes. You actually have, well, let's just talk about that in a little bit. You actually have quite a few more outcomes to deal with. It might take you up to 20, which I believe that's what I actually had you guys do next. Up to 20 outcomes, and it's going to cost you roughly $21.60. So these are the two answers to the two middle questions on the quiz. Equals sum of all probabilities. Now notice it's getting better. You're getting better. I should turn my Outlook off, but it's still not 100% yet. In order for it to be 100%, you'd have to continue this pattern down forever. Forever and ever and ever. Which means, look at this column. This is the contribution to the average with each additional trial. Notice how each additional trial is getting slightly larger each time? That means the overall average is getting slightly larger by each of those increments each time. The last question, on average, how much does it cost to make back your dollar? There is an infinite amount of money necessary on average to win back your dollar because there is no bound. There is no bound on how this thing is going to grow. It's going to keep growing infinitely. It's called a divergent series in calculus, if you've taken calculus before. But even if you haven't, you can see why it diverges. Why it diverges. Sure, the chance of each of the probabilities, the probabilities of it taking an additional roll each time is basically a half, but a half as likely as the one before it, but you're doubling down your bet. This is exactly twice as big as that. This is a little bit less than half as big as this, which means this guy's creeping up with each successive thing. Notice that's getting approximately equal with each successive one, but it's not exactly. It's honing in closer, the limiting values there. But this thing's getting bigger each time, which means the sum is getting bigger each time. It's a pretty amazing. It's called a geometric series, and the reason it's so interesting mathematically is, theoretically, you can lose on an infinite number of rolls before you win. Now that sounds stupid, an infinite number of rolls before you win. Well, yeah, mathematically, I mean, you could keep crapping out. I mean, you could roll snake eyes 2 or 3 on the first roll, or lose on the point bet. It only happens 50.7% of the time, but you could actually have that happen every single trial. And in which case you keep doubling down and doubling down. This bet right here by itself, I mean, you can think about what that bet is. It's a $1 million bet. The next bet doubled down is a $2 million bet, and then a $4 million, and then an $8 million, and then a $16 million. And pretty soon you're betting billions of dollars and trillions of dollars. You're betting the national debt. So that's what's so interesting about this problem, is that the gambler's ruin, why it's called the ruin, is because eventually you're gonna bankrupt yourself. On average, you have to bankrupt yourself because there's not enough money in the world to make your dollar back on average. Pretty fun problem. Hope you enjoyed it as much as I did.